Managing memory. In this nugget, we're going to do a little bit of review just to make sure that we're on the same page in terms of understanding the Oracle memory structures. But then we're going to deep dive into memory parameters, both for the SGA as well as the PGA. How to do the tweaking manually if you're so inclined, but of course Oracle's own suggestion is to let Oracle take care of managing all of those various memory caches and buffer areas. We'll understand by the conclusion of this nugget what the difference is between AMM, that stands for Automatic Memory Management, and ASMM, that stands for Automatic Shared Memory Management. Boy, there's a lot of TLAs and FLAs in this course, aren't there? That stands for 3-letter acronyms and 4-letter acronyms, respectively. Without any further ado, let's get rocking. Now, what are the basics of memory with Oracle Database? Memory, as you know, can be either physical or virtual. Physical memory deals with the random access memory modules installed on our server's motherboard. RAM is scratch space. It's going to be super high speed temporary storage that, well, really our computer as a whole uses, doesn't it? The operating system uses it, any installed applications and processes use RAM, and of course Oracle Database 11G is no different. Historically, the paging file, or virtual memory, or VM as it's sometimes called, frankly VM now tends to mean virtual machine in a virtualization infrastructure as opposed to virtual memory. But this was a way, and still is, ironically and strangely enough, a way to extend physical memory such that the computer theoretically won't hit a top end in terms of its RAM usage. In other words, it won't run out of memory. We may have nowadays 4, 8, 16 gigabytes of physical RAM, which is a tremendous amount, especially when you consider that just a handful of years ago, to have 16 megs or 32 megs of RAM was a big deal. But we can make use of a physical file called the paging file or the virtual memory file, depending upon your operating system, to take less frequently used data blocks, if you don't mind my word salad there, page them out to disk, which is going to give much slower I/O, of course, but the idea is if the application needs those data pages, we can put them back into high-speed, high-access RAM by just pulling from the page file. All of that is really just a history lesson, and it's important in a way, and it's intellectually a curiosity, but as far as Oracle Database goes, it doesn't know, it doesn't care whether it's pulling RAM physically from our RAM modules or virtually from the paging file. It can't differentiate it. All Oracle needs to know is how much RAM we're going to give it, and also whether we're going to let Oracle manage the RAM, or memory really is what I should say, or if we as administrators want to specify or pool out those different memory pools. And as we're going to see in the next whiteboard slide, Oracle has a plethora of different pools and caches. Really, cache and pool mean the same thing. It's just going to be basically an area marked out for Oracle to use allocated memory in a particular way. Now, if you're a typical system administrator, and I mean that with love and respect, not with any insult to your intelligence, but if you're a typical administrator who's really busy doing a lot of different things, you're of the mind, well, if we feel that our application is constrained for memory, throw more memory at it. More memory is, generally speaking, a good thing and is going to give your server more breathing room. Well, with Oracle, it's important to understand that just throwing more memory at it is not necessarily a good thing. There's an entire voodoo science, for lack of a better term, on memory optimization in Oracle. I want you to know by way of disclaimer, we're simply scratching the surface in this nugget and the other nuggets in this course. You can develop an entire career focusing on Oracle performance tuning and optimization. As it happens, if you're not tuning these memory caches correctly, you're going to hobble your Oracle server's performance. This is the main reason why Oracle themselves, the company, suggests that we use automatic memory management instead of getting in there and manually tweaking those parameters ourselves. Our memory structures in Oracle are divided into two main categories: the System Global Area, or the SGA, and the Program Global Area, also called the PGA. Let's pop on out to the Oracle documentation and take a look at a figure. This is showing the Oracle database memory structures, and this is a pretty popular and pretty common diagram. It shows, first of all, each server process attached, generally speaking, to a user, but there's also server processes spawned by Oracle itself. We've covered some of those recently in terms of using RMAN and how RMAN uses processes and threads, but in this case, we'll assume that process 1 and process 2 are spawned for individual users. Users get their own program global area. PGA consists of a couple components that we'll talk about in just a moment. The system global area, there's going to be one of these per database, and in the SGA, this is the shared memory area for the entire database, consists, as I said, of several caches and pools. We'll describe those briefly in just a moment again. Come back to our whiteboard. I'm actually going to start with the PGA here because it's a little bit simpler. The content of the program global area is session memory and the private PGA. Session memory is memory that's allocated to host the user's logon environment. They're session level variables. You remember we can alter system or alter session to change parameters in SQL+. If you're running Oracle in a shared server configuration, the session memory is shared and not private to each user, even though it's part of each user's PGA. Another element that's in the session memory is called the call stack, and this allows the user to use the up and down arrow keys to re-invoke previous commands that they've put in there. The truly private SQL area contains stuff like execution plans, bind variables, and temporary tables. Bind variables are input parameters that the user adds to their queries and PLSQL code. So that's that. That's memory allocated to each user. And you see there are quite a few plates spinning and quite a few moving parts here, all of which is virtualized on a per process basis. It's pretty crazy. Over on the SGA side of the fence, we have a couple extremely important memory areas. We're going to cover these in separate whiteboard slides, actually. The database buffer cache and the redolog buffer. I'm actually going to hold off any further discussion of those until we get to those whiteboards. With respect to our various pools, shared pool, large pool, streams pool, and Java pool, of these four, you might be thinking, well, what the heck is going on in each one of these memory areas? Why are there so many of these pools, number one, right? Well, the shared pool consists of three sub-caches: the library cache, the dictionary cache, and the result cache. This is where execution plans, PLSQL program units, and data dictionary information is kept in memory. A lot going on in the shared pool. The large pool contains shared server session memory, I/O server processes, and for our purposes at the OCP level, your Oracle database backup and restore operations are stored in the large pool. The streams pool is used by Oracle Streams, buffer queue messages, and Oracle Streams capture and apply processes. Java, pretty easy, just by this word, should tell you that this is where Java virtual machine data is stored. Now again, where do you go with all this? How do we as an administrator control all of these memory structures on a daily basis? Well, for the purpose of the exam and the purpose of making your lives as easy as possible, let's review the initialization parameters that govern automatic memory management and automatic shared memory management. First, let's look at the global top-level parameters. The main one to remember, if you decide to let Oracle cover allocation of memory to all of those different pools and caches, is you want to set the memory underscore target initialization parameter. This is a dynamic parameter which means we can keep the instance and database online and open as we manually change the target. That's good news because if we feel that our memory is getting a little bit tight, we can boost this value without downing the database. Now, here's potential point of confusion. Some administrators wonder what the difference is between the memory target initialization parameter and the memory max target. Max target actually is a static parameter that you need to bounce the database in order to make a change here to go into effect. Basically, max target gives you a line in the sand. For instance, you might say, and I'm just pulling these numbers out for the sake of ease of use, that we're going to set a memory max target of 800 megs. And our current memory target we'll put it 600 megs. So for max target, we're saying, okay, this is our drop dead value. We never want Oracle to exceed this value because we would reduce the stability of other applications on that server, or perhaps reduce the stability of the entire server. That gives us some wiggle room here in terms of adjusting the memory target in a dynamic fashion. We can now work, if we decide to, boost it up to 750, bring it down to 500. We have some play there. Do you see what I'm saying? So that's the distinction between the max target and the target. By setting memory target, you're telling Oracle you want it to manage all of your SGA and PGA, all of your automatic memory needs. Now, Oracle gives us a midline to go, with the two extremes being one, automatic memory management, where Oracle takes care of all memory allocations, and the other extreme being completely manual memory management, where you set those initialization parameters separately. The midpoint would be to dive into the SGA and PGA individually and set caps there. To go over to the PGA side, there's an init param called PGA aggregate target that serves as a top level value for just the PGA. On the SGA, you have analogous dynamic and static parameters. SGA target provides a dynamic value for SGA and all of the pools underneath there, the various SGA caches. SGA max size is a static parameter that provides the line in the sand that we talked about earlier. Okay, you see how that works? So you either tell Oracle to do everything, you get down and separate PGA and SGA and put individual caps on it, or you go the completely manual route. It's up to you. Now, before we go into the demo, let's discuss in a little bit more detail the database buffer cache and the redo log cache, just because they're so important for an Oracle performance tuning standpoint. By way of review, you'll remember that the database writer background process, DBWN, writes blocks from the buffer cache to your data files. So the Achilles heel, so to speak, in the Oracle system is a change happens, and that change, that transaction, it could be an insert, update, delete, whatever, some kind of DML or even DDL, temporarily exists only in memory, in the buffer cache, such that if the server were to lose power or suddenly crash at that point, well, those changes are going to go up the flue, aren't they? So that's what I always call the Achilles heel of Oracle. So the deal is we want to get those blocks written permanently to the data files, or at the least the redo log files, as quickly as possible. So the database writer uses what's called a lazy algorithm to write those blocks from memory in the database buffer cache permanently to the data files. Now, the data states in that buffer cache, there are many-fold, really. There are free blocks that are unused. There are pin blocks where you can actually maintain data in the buffer cache for extended periods of time. This would be useful, for instance, for execution plans and PLSQL procedures that are frequently being run. Indexes are another opportunity to keep data persistently in a buffer cache. You'll see I have some sample code down here that shows us pointing an index to a particular buffer pool. Clean and dirty blocks refer to whether a block has been written to the data file or not. That Achilles heel I mentioned are dirty blocks, where we have volatile changes in memory that hasn't yet been written to the data file or the redo log stream. You'll often hear, both in the literature or if you're just at a user group, whatever, talking to other Oracle DBAs, techniques for adjusting or increasing the cache hit ratio. Here's the deal. It's kind of a two-sided coin. On one hand, you want your data blocks to get into the data files and redo log files as quickly as possible, but on the other hand, you want frequently accessed data to stay in the buffer cache such that additional queries for that data come out of the cache, as opposed to having Oracle having to pull those blocks from the data files. Remember at the beginning of this nugget I mentioned how much faster data access is when we're pulling from RAM as opposed from the disk, you see? So we want a high cache hit ratio, and if we're getting a lot of cache misses, that could be an indication that we don't have our buffer cache sized properly. And that could point ultimately to not enough physical RAM. Remember what I said earlier, that just throwing RAM at Oracle isn't a be-all, end-all solution, but don't minimize the possibility that your server may actually be hungry or starved for more RAM, all right? Finally, we have the redo log buffer, and the way this works, you'll recall, is we have a memory area to store the actual commands, the DML commands that result in those changed blocks that are captured in the database buffer. The redo statements are transitioned using the log writer process to the redo log files. So in other words, we have a volatile memory area, the redo log buffer, and we want to get that data, those statements, recorded into the redo log files, the non-volatile stream, as quickly as possible. Now remember I mentioned that the database buffer that's actually storing the changed blocks uses a lazy writing algorithm, so it's not writing as aggressively as logwriter is. And it makes sense when you think of that. The actual SQL that generates those changed blocks is what we need in the event that we have to use redo to roll forward changes, right? So in a sense, the actual SQL is more important than the changed blocks, at least in the short term. So therefore, logwriter does its thing as far as purging the redo log buffer and getting that SQL into the redo log stream whenever a transaction is committed. And as you know, commits happen automatically under many circumstances in Oracle, or we can use the commit statement in our code. Every 3 seconds, logwriter does a flush. Also, if the redo log buffer becomes 1/3 full. So that should give us as administrators a pretty good degree of security that in the event of a failure, we should be able to resurrect those changes, if no other place than the redo log stream. And that, yet again, for like the 500th time, underscores the importance of running your database in archive log mode and making sure that you're keeping a historical record of your online redo log files. Now, what are some tips to increase performance? One is to do batch commits. Instead of committing every transaction atomically, you can improve performance by issuing a commit explicitly in your code after several DML statements. Now, what's the advantage? Well, you have logwriter doing one thing instead of repeating the same action multiple times that is going to degrade performance over time. The other suggestion for Oracle is to temporarily turn off redo logging when you're bulk loading data. Now, on one hand, you might think, well, isn't that a risky proposition? Yes and no. No, because you can always redo the bulk load if something goes kerflunky. You like my technical language there, kerflunky? Number two, you might want to take that small calculated risk at not logging this operation in order to counterbalance the speed improvement that will happen in terms of being able to do a bulk load without having logwriter have to boom, 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 commit and flush over and over again. Does that make sense? All right, so we're going to do a brief demo now. I'll give you a tour of the memory advisors and show you, if you really want to, how we can manually specify those memory initialization parameters. Let's get to work. Hey there, welcome to this demo on memory management in Oracle Database 11g. As you see, I've logged into SQL Plus as the sys user, and let's start this demonstration by examining the contents of our SGA components through SQL. Believe me, it's much less painful to do this through Enterprise Manager, but I want to just share with you some of the relevant $V dynamic performance views that come into play. This first query you see here, I'm querying $V memory dynamic components and pulling back 3 columns. Component, current size, actually just 2 columns, sorry, component and current size. And it breaks it down for us, doesn't it? The various SGA pools and caches. This is an extremely still system. That explains all of the zeros that you're seeing here. But that report's really nice and really relatively easy to run in comparison to some of the others. For instance, if you want to see the last 800 or so SGA resizes that Oracle's performed, you'd want to query the $view $memory underscore resize underscore ops. That, of course, stands for memory resize operations. If you're interested in seeing buffer cache hit ratios, the relevant DMV there, or DPV, dynamic performance view, is $sysstat, SYSSTAT. You can get buffer cache advice as well by querying $db cache advice. There's quite a few dynamic performance views that are helpful, but like I said, you don't need to know all of those for the exam. You just need to know the relevant memory parameters as well as some facts about navigating the memory advisory framework in Enterprise Manager. You see, I've run show parameter memory to bring back our automatic memory management initialization parameters. There's memory target and memory max target. You see on my system that I've set my memory target to the max target. So I can certainly resize memory target downward in a dynamic fashion, but if I feel that Oracle needs more than 900 megs, it looks like we're going to have to change memory max target and bounce the database. As far as the individual caches and pools, you can check the Oracle documentation for their names. It's pretty straightforward. DB underscore cache size is the database buffer cache. Shared underscored pool size is for the shared pool. Basically, if you did want to disable AMM, you would want to set your memory target to 0, if you wanted to do this through SQL, that is. And then you would just set your pools and caches individually using alter system set and then the name of the pool. The Java pool is Java underscore pool underscore size. You remember for PGA, there's PGA aggregate target and so forth. All that's pretty painful though, quite honestly. If we want to switch our focus over to Oracle Enterprise Manager, we can access the memory advisors as well as our initialization parameters. The latter can be seen graphically on the Server tab under Database Configuration. We can just hit up initialization parameters, and instead of using show parameter, we can simply run a query here for those relevant parameters. There's so many in the list, of course. We can make the changes there. Alternatively, if we want to get into the memory advisor framework, there are many entry points to that. From the Server page in Enterprise Manager, we can click Memory Advisors to go directly into the advisors. Alternatively, from say the availability page, we have a link to Advisor Central, which we looked at in the previous nugget. That shows us all of the advisory frameworks. And from here, we can click Memory Advisors to go directly into it. Now, first you'll see automatic memory management is either disabled or enabled. I have mine disabled on my system, and with one click of the mouse, I can switch that. Now, if we do that, we're asked to specify a maximum memory size and a total memory size. These are those two parameters we talked about, right? Memory target and memory max target. And it tells us if we change the memory max target, we're going to have to restart the database. I'll leave these values alone right now. And now we have some pretty pictures to look at, which are fine and dandy if you're not colorblind. However, I am colorblind, so I can see shades, gradations. So in this first chart that shows us over the last couple hours or the last hour or so our allocation history between PGA and SGA, I can see that our SGA is just marginally higher in RAM or memory utilization than is my PGA. Oh, before we go on, I want you to see that this advice button is awfully useful in terms of helping you tune your maximum memory. Let me click that actually. And what this will do is open up a little browser window that shows you, again, it's color coded unfortunately, the percent improvement you can expect based on moving your memory size. Now the little X denotes your total memory. Whatever color this is our maximum memory, our line in the sand, and of course it's the same value on this system. I have my max mem and my mem target set to the same thing. But what this is telling us is if we were to throw more RAM at Oracle, we're not going to necessarily see any performance improvement. Now remember, this is a stock system that's about as quiet as a church mouse. So this speaks to that suggestion that simply throwing RAM at Oracle willy-nilly isn't necessarily going to help us. By contrast, you notice that our performance is expected to drop precipitously if we set our memory below, say, it looks about 700 megs. If we brought it down to 400, we would just be in the tank as far as performance. Please don't underestimate how powerful the advice button is, and you'll see it periodically throughout the Oracle Advisory Framework. If we scroll down to the bottom of this page, page. It's a tabbed interface where we can examine SGA and PGA individually. On SGA, we see an allocation histogram. On my system, it looks like shared pool and buffer cache are saving the day with everything pretty much. Down at the very bottom, we see a little bit. I think this denotes the large pool, which would deal with basically any PLSQL packages and jobs that are running automatically, because I don't have anything running manually on this particular system, and I'm not making use of the Java virtual machine, so we shouldn't see anything there. And actually, if you want the specific numbers for your SGA allocation, that's what this current allocation area is for, that shows us graphically in a pie chart, as well as giving us the actual numbers and percentages. This is what I like, being colorblind. That shows us Java pool is 0.7%, large pool is 0.7 as well, and that's about that. PGA, there isn't as much to look at. If we switch over to the PGA tab, basically we have the aggregate target, which is disabled in an automatic memory management framework. We can set that if we turn off AMM. It tells us our current PGA allocated and our maximum, same value. This is what Oracle's using internally, as well as, this is an important metric, the cache hit percentage. Nice, easy way to get to that. So that's really it, friends. Not all that much to it. In sum, what I want to say is, if you want a good lesson or something to help you appreciate how powerful automatic memory management is, get your hands on an early edition of Oracle Database. That is, an edition before AMM was introduced. Because in those days, Oracle DBAs had no choice but to individually set and juggle all of your memory caches and pools. And that's no fun, believe me. Managing memory review. Boy, we covered a lot of ground in this nugget, didn't we? It was basically a mini review of many of the memory architecture concepts that we covered in much greater detail in the DBA 1 CBT Nuggets course. At this point, you should be really refreshed on what the memory structures are in Oracle Database 11g, paying particular attention to the SGA and PGA, of course. You understand the initialization parameters that control those memory pools, both individually, as well as how we can round those values up by setting up just a couple of them instead, like automatic memory management or automatic shared memory management. I hope I made a good case for letting Oracle take care of memory, but you also have the skills and tools to step in and do manual intervention if need be. I hope that this has been informative for you, and I'd like to thank you for viewing.